Welcome to this audiobook summary of Stephen Hawking's groundbreaking work, A Brief History of Time. In this compelling narrative, Hawking invites listeners on a fascinating journey through the cosmos, exploring profound questions about the nature of the universe, time, and existence. Originally published in 1988, this book has captivated millions around the world, becoming a cornerstone of popular science literature. In this audiobook, we'll break down Hawking's complex ideas into easily digestible segments, covering key themes such as the evolution of cosmological thought, the implications of the Big Bang Theory, the mysterious nature of black holes, and the quest for a unified theory that could reconcile the principles of quantum mechanics with general relativity. Listeners will discover how Hawking explores the fundamental laws of the universe, the intriguing concept of time, and the philosophical implications of scientific discoveries. This summary is designed to provide you with a clear understanding of Hawking's insights while also highlighting the book's significance in the realm of science and philosophy. Join us as we dive into the remarkable ideas presented in A Brief History of Time, uncovering the mysteries of the cosmos and our place within it. Part 1. Introduction and Early Concepts of the Universe. Stephen Hawking's A Brief History of Time opens with a brief overview of the history of our understanding of the universe. In this section, Hawking explores early cosmological views and theories from ancient civilizations to the dawn of modern science, covering the evolution of thought on the cosmos and humanity's place within it. Early on, ancient societies often conceived of the universe in simplistic terms, largely viewing it as a finite, stable structure ruled by gods or mystical forces. By the 17th century, science began to replace mythology and religion as the primary means of understanding the cosmos. This shift largely took place with the pioneering work of figures like Galileo Galilei and Isaac Newton. Galileo's telescopic observations allowed scientists to view celestial bodies in new detail, while Newton's laws of motion and universal gravitation provided a groundbreaking mathematical framework. His theories suggested a mechanistic universe that operated according to predictable laws, laying the foundation for classical physics. This part also introduces Albert Einstein and his revolutionary contribution to our understanding of time and space through his theory of relativity. Einstein's work fundamentally changed the way we understand gravity, demonstrating that it results from the curvature of space-time rather than an invisible force. These discoveries marked a dramatic shift from Newtonian physics, leading scientists to explore new and complex models of the universe. Hawking establishes a core theme here: the interplay between observation and theory in shaping our cosmological models. This sets the stage for the journey into the quantum and relativistic domains that will dominate much of the book. He also addresses how breakthroughs in physics have continually transformed our understanding of fundamental questions about time, space, and existence itself. Part 2. The Expanding Universe and the Big Bang Theory. In the second part of A Brief History of Time, Hawking delves into one of the 20th century's most significant discoveries, the expanding universe. This finding reshaped modern cosmology, suggesting that the universe is not static as previously thought, but dynamic and continuously evolving. The idea of an expanding universe emerged from the work of astronomer Edwin Hubble, who observed that distant galaxies were moving away from us, with their speed increasing relative to their distance, a phenomenon known as the redshift. Hubble's findings provided the first solid evidence that the universe had a beginning and could be traced back to a singular origin. This discovery led to the development of the Big Bang Theory, which posits that the universe began as an extremely hot, dense point approximately 13.8 billion years ago. From this initial state, the universe has expanded over time, cooling and evolving into the vast cosmos we see today. Hawking explains how the Big Bang Theory not only provides a scientific narrative for the origin of the universe, but also raises profound questions about the nature of time and space. In this early stage, time as we know it may not have existed in the same form, challenging the very concept of causality. To illustrate these ideas, Hawking introduces key concepts from Einstein's general theory of relativity, which explains gravity in terms of curved space-time. According to general relativity, the Big Bang could be viewed as a singularity, a point where all known laws of physics break down, creating a boundary to time and space. This singularity presents a paradox for scientists, as it suggests a beginning without a prior cause, which is difficult to reconcile within the standard framework of physics. Hawking highlights how these insights into the expanding universe and the Big Bang Theory spurred deeper investigations into the cosmos. Cosmologists began exploring phenomena such as black holes, which, like the Big Bang singularity, challenge the limits of our understanding. He underscores that studying these extreme conditions can reveal clues about the fundamental nature of the universe, motivating scientists to pursue a unified theory that combines quantum mechanics with general relativity. Part 3. Black Holes and Singularities. In this section, Hawking explores one of the most fascinating phenomena in the universe: black holes. Black holes are formed when massive stars collapse under their own gravity, compressing matter into an incredibly dense point known as a singularity. Hawking describes how, within a black hole, gravitational forces are so powerful that not even light can escape, creating an event horizon, the boundary beyond which nothing can return. Hawking explains how black holes serve as natural laboratories for studying extreme gravitational forces, where both general relativity and quantum mechanics seem to apply but don't reconcile easily. This conflict between the two theories highlights the need for a unified framework that can describe gravity at both cosmic and subatomic scales. Black holes thus play a crucial role in theoretical physics, as understanding their behavior may help bridge the gap between these fundamental theories. A key concept introduced here is Hawking radiation, which was one of Hawking's most groundbreaking contributions. In the 1970s, Hawking theorized that black holes aren't entirely black but emit tiny amounts of radiation due to quantum effects near the event horizon. This radiation causes black holes to gradually lose mass and potentially evaporate over time. This surprising revelation suggested that black holes could eventually disappear, raising questions about the fate of the information contained within them, a problem known as the information paradox. Hawking discusses how his discovery of Hawking radiation challenged existing theories, as it implies that information could be lost when a black hole evaporates. This idea contradicted the principle of quantum mechanics that information should always be preserved, sparking intense debate in the scientific community. The information paradox remains one of the most significant unresolved issues in theoretical physics, symbolizing the clash between quantum theory and general relativity. Hawking's examination of black holes provides a deeper understanding of the universe's most extreme phenomena and emphasizes the need for a theory that can unite the forces governing large cosmic structures with those governing microscopic particles. This exploration into black holes and singularities also underscores the mysterious and potentially finite nature of time and space. Part 4. The Uncertainty Principle and Quantum Mechanics. In this section, Hawking introduces the principles of quantum mechanics, which govern the behavior of particles at the smallest scales. One of the foundational concepts in quantum mechanics is Heisenberg's uncertainty principle, which states that it's impossible to simultaneously know both the exact position and momentum of a particle. This inherent uncertainty challenges the deterministic nature of classical physics, as it suggests that at the quantum level, events can only be described in terms of probabilities rather than absolute outcomes. Hawking explains how quantum mechanics transformed our understanding of the universe, revealing a realm where particles behave in ways that defy intuition. Particles can exist in multiple states or locations at once, a phenomenon known as superposition, and they can become entangled, meaning their properties become interdependent even over vast distances. These strange properties suggest that the fundamental nature of reality is not as straightforward as it seems on the macroscopic scale. The uncertainty principle also plays a crucial role in the behavior of black holes and the formation of Hawking radiation. When quantum effects are considered near the event horizon of a black hole, particle-antiparticle pairs can spontaneously appear, with one particle escaping as radiation while the other falls into the black hole. This process is part of what causes black holes to lose mass over time, as explained earlier, providing a bridge between quantum mechanics and general relativity. However, integrating quantum mechanics with general relativity is one of the most challenging aspects of modern physics. While general relativity governs the large-scale structure of space-time, quantum mechanics rules the atomic and subatomic scales, leading to conflicting predictions about the nature of reality in extreme environments, such as near black holes or the Big Bang singularity. This inconsistency points to the need for a unified theory of everything that can encompass both frameworks. Hawking emphasizes that any future theory uniting quantum mechanics and general relativity would likely revolutionize our understanding of the universe, enabling us to answer questions about the origin of time, the nature of singularities, and possibly the entire structure of reality. This exploration of quantum uncertainty and its implications reveals the limits of human knowledge and the tantalizing mysteries that still lie beyond current scientific understanding. Part 4. The Uncertainty Principle and Quantum Mechanics. In this section, Hawking introduces the principles of quantum mechanics, which govern the behavior of particles at the smallest scales. One of the foundational concepts in quantum mechanics is Heisenberg's uncertainty principle, which states that it's impossible to simultaneously know both the exact position and momentum of a particle. This inherent uncertainty challenges the deterministic nature of classical physics, as it suggests that at the quantum level, events can only be described in terms of probabilities rather than absolute outcomes. Hawking explains how quantum mechanics transformed our understanding of the universe, revealing a realm where particles behave in ways that defy intuition. Particles can exist in multiple states or locations at once, a phenomenon known as superposition, and they can become entangled, meaning their properties become interdependent even over vast distances. These strange properties suggest that the fundamental nature of reality is not as straightforward as it seems on the macroscopic scale. The uncertainty principle also plays a crucial role in the behavior of black holes and the formation of Hawking radiation. When quantum effects are considered near the event horizon of a black hole, particle-antiparticle pairs can spontaneously appear, with one particle escaping as radiation while the other falls into the black hole. This process is part of what causes black holes to lose mass over time, as explained earlier, providing a bridge between quantum mechanics and general relativity. However, integrating quantum mechanics with general relativity is one of the most challenging aspects of modern physics. While general relativity governs the large-scale structure of space-time, quantum mechanics rules the atomic and subatomic scales, leading to conflicting predictions about the nature of reality in extreme environments, such as near black holes or the Big Bang singularity. This inconsistency points to the need for a unified theory of everything that can encompass both frameworks. Hawking emphasizes that any future theory uniting quantum mechanics and general relativity would likely revolutionize our understanding of the universe, enabling us to answer questions about the origin of time, the nature of singularities, and possibly the entire structure of reality. This exploration of quantum uncertainty and its implications reveals the limits of human knowledge and the tantalizing mysteries that still lie beyond current scientific understanding. Part 6. The Nature of Time. In this section, Hawking examines the concept of time itself, exploring how it differs from space and why it appears to flow in a single direction, from past to future. Time, as understood through general relativity, is part of the fabric of space-time, curving in response to matter and energy. This relationship suggests that time and space are intertwined, not separate, and that the movement of matter through space affects how we experience time. One of the central ideas here is the concept of arrow of time, which Hawking categorizes into three types. Thermodynamic arrow of time. Based on the second law of thermodynamics, this arrow states that in any closed system, entropy or disorder tends to increase over time. This is why events in our daily lives seem irreversible. Things naturally move from order to disorder, like ice melting or coffee cooling. Psychological arrow of time. This is the way we perceive time, feeling it pass in a single direction, from past to future. Our memories are of the past, and we anticipate events in the future, which aligns with the thermodynamic arrow. Cosmological arrow of time. This arrow points to the direction in which the universe itself expands, tied to the Big Bang and the continuous expansion of space. As the universe grows, it defines a directional flow in time. Hawking explores the fascinating idea that if the universe were to contract rather than expand, the cosmological arrow of time might reverse. However, he points out that this wouldn't necessarily change our psychological arrow. Human experience would likely remain as it is, bound to the forward progression of time as we understand it. These different arrows of time reinforce the notion that time is more than just a simple measurement. It has fundamental physical, psychological, and cosmological implications. Hawking also raises the possibility that time had a beginning at the Big Bang, where it emerged alongside space. If so, questions about what existed before the Big Bang may be meaningless, as time itself did not exist. Hawking's exploration of time further illustrates the limits of human understanding when it comes to the universe's origins and nature. The laws governing the macroscopic world, like thermodynamics, do not always apply in the same way at the quantum scale or in extreme cosmic settings, leaving us with profound mysteries. Understanding the true nature of time could ultimately be key to unlocking the secrets of the cosmos and may provide a deeper insight into the ultimate questions surrounding existence. Part 7. The Future of Cosmology and Final Reflections. In this concluding section, Hawking reflects on the future of cosmology and humanity's quest for knowledge. He reiterates the significance of discovering a unified theory that could reconcile the laws of general relativity with quantum mechanics, a goal that, if achieved, would revolutionize our understanding of the universe. Hawking is optimistic that such a breakthrough could happen within a few decades, given the pace of scientific progress and advancements in technology. He believes that this unified theory could provide answers to questions about the origins of the universe, the nature of time, and the ultimate fate of everything. Hawking also discusses the implications of such knowledge for humanity. He argues that understanding the laws governing the cosmos is not just about science. It is part of a larger quest for meaning and place within the universe. A theory of everything would not just be a scientific achievement, but a philosophical revelation, shedding light on the fundamental mysteries of existence and the nature of reality itself. Additionally, he speculates on the future of space exploration and the role it might play in humanity's survival. As our understanding of the universe expands, so too does the potential for exploring and possibly inhabiting other planets. Hawking views this as essential for the long-term survival of humanity, particularly in the face of potential existential threats on Earth. He encourages continued investment in space research, suggesting that one day humans may live among the stars, expanding our presence throughout the cosmos. In his final reflections, Hawking expresses hope that one day, humans will achieve a complete understanding of the universe. He suggests that knowing the mind of God or the fundamental blueprint of the cosmos may ultimately be within our reach. Such a breakthrough would fulfill humanity's most ancient curiosity, answering the question of why we and the universe exist at all. However, he leaves open the possibility that each new answer may lead to even deeper questions, underscoring the endless nature of exploration and discovery. A Brief History of Time concludes by reaffirming that the pursuit of knowledge is as much a part of a human experience as the questions it seeks to answer, driving us to continually push the boundaries of understanding and wonder about our place in the vastness of existence. This ending encapsulates Hawking's lifelong dedication to unlocking the mysteries of the universe and sharing its wonders with the world. As we conclude this audiobook summary of A Brief History of Time, I encourage you to delve into the book itself for a more comprehensive understanding of Stephen Hawking's groundbreaking ideas. While this summary provides an overview of key themes and concepts, the full text offers a richer exploration of the intricate theories and thought-provoking questions that Hawking presents. Hawking's ability to convey complex scientific principles with clarity and passion makes the book not just an intellectual endeavor but an inspiring journey into the depths of the universe. Reading A Brief History of Time will deepen your appreciation for the cosmos and may ignite your curiosity about the fundamental questions of existence. Whether you are a seasoned science enthusiast or a curious newcomer, Hawking's insights are sure to resonate and provoke further contemplation. Don't miss the opportunity to experience the full brilliance of Hawking's work. Pick up a copy of A Brief History of Time and embark on a fascinating adventure through time and space.